Alright, so now you've written code to compute the cost of a particular warping path by summing all of the distances in the cross-similarity matrix that it passes through. Now you can certainly check every single possible warping path and then report the one which minimizes those sums. That would be very inefficient. We would call that a brute force approach. And it turns out there's a more efficient way to do this using something called dynamic programming. And I'm not going to go into the details of the correctness of this. If you're curious, though, I'll link to some resources that I gave my algorithm students proving the correctness of algorithms like this. And maybe that'll excite you to take algorithms if you haven't already. Okay. But for now, I'm just going to state something without proving it that we're going to use to compute the warping path. Now, before we actually compute the optimal warping path, what we're going to do is actually compute just the minimum cost of an optimal warping path. And then we'll be able to kind of turn this algorithm on its head to extract the warping path itself that realizes that. Okay, so let's say that we start, let's consider a cross-similarity matrix C. And let's also consider the minimum cost warping path that starts at 0, 0 and ends somewhere in the middle and ends at ij. So we're not going to necessarily go all the way to the end, the lower right corner of the cross-similarity matrix, but we'll insist that we actually end somewhere in the middle at a particular row I, particular column j. We'll call the optimal cost over all such warping paths Sij. So the S, I guess, refers to cumulative sum over all the warping path correspondences from 0, 0 to ij. Okay. So then we have this recurrence relation. Then the following, it's called recurrence relation. Recurrence relation can be used to compute Sij. So we're going to compute a particular Sij. And we're going to say the following. Sij is the min of, I'm going to write some fancy LaTeX here, but I'm just going to make a little table. Okay. So there are three options. So we look at Si minus 1j. We also look at Sij minus 1. And we also look at Si minus 1, j minus 1. Okay, let me make sure the LaTeX was looking good here. Okay, it is. So what you do is, okay, look, I'm trying to figure out what is the minimum cost over all possible warping paths that start at 0, 0 and end at ij. Well, if I know actually what the minimum cost over all warping paths that start at 0, 0 and end at I minus 1j, and I know that the same thing for I and j minus 1, and I know the same thing for I minus 1, j minus 1, then I can compute this. And actually, after that, I have to sum to it the cross-similarity matrix at ij. Okay. So basically, I consider, you can really think about this intuitively, as I consider three options. The warping path either came from above me, so that's I minus 1. It either came from the left of me, or it either came from this diagonal to the left and above me. And I say, well, which one of those would have been the best to do? And then I say, okay, well, now I end up in ij, so I have to add to whatever the best of those was. You know, I go up from the beginning up to one of these. Now I'm going to move to ij. And I'm satisfying my warping path rules, right? I know my warping path can only move by I plus 1j, ij plus 1, or I plus 1, j plus 1. Oops, I had a typo there. There we go. So So we see that would satisfy, coming from each one of these would satisfy that continuity condition. Okay, but this is also, this observation is itself an algorithm, because I can actually compute every possible ij using this. And what I'm looking for in the end is a path which ends up at the lower right hand corner. So what I'm looking for in the end is s of m minus 1, m minus 1. So this gives us an algorithm to compute this. We just compute all the smaller subproblems first, and then we end up with this full solution. So I'm going to write this in code, and I'll show you what it is. But so I'm assuming that we have some cross-similarity matrix. So I made this example with the figure eights up here. So I say C is equal to get CSM fast y1, y2. Okay. Now I'm going to make a matrix S, which has the same dimensions as C. Okay. Now S 0, 0, that's just a warping path that starts at 0, 0 and it ends at 0, 0. Well, this one's pretty simple. That should just be the best I can do. There's only one possibility. It's just going to be the cost. It's just going to be the distance from point 0 and 1 to point 0 in the other one. Okay. So this is called my base case. All right. Let me get, there are other cases I should get out of the way, actually. So I'll say let me get the first row out of the way. So first row. These are all the warping paths that only match a single element of the first point cloud to some number of elements in the second point cloud. So let me get that out of the way too. So I'll say for j in range, let me just define these variables. M is the number of rows, c dot shape 0, number of rows, and n is the number of columns. Okay, so I'll say, I'm going to go through all the columns, and I'll say S. Well, actually, I can do this quickly with NumPy. I can just say that S, the first row. Well, let me write it clearly with a loop first. So I'll say, yeah, for j in range 1 n, S of 0 j is equal to S of 0 j minus 1 plus C of 0 j. So I have to match everything to the first point in the first point cloud, in the first row there. Now I can write this more efficiently as simply S, the first row, is equal to the cumulative sum of the first row of the cross-similarity matrix. That's a more efficient way to write this. So I'll keep this here in comments, but I just want to, I'm going to do this a slightly more efficient way. And I can do, whoops, sorry, that's the cumulative sum. Okay. I could do a similar thing for the first column. I could say, well, that's the cumulative sum of the first column of the cross-similarity matrix. Okay. I'm just getting out of the way some of the base cases. All right, where it's almost kind of trivial. It's like I'm matching just the first point of the first point cloud to some number of points in the second point cloud, and vice versa. Okay. Now let me loop in the middle. Let me assume that I and j are both greater than 0 here. Okay, so say for I in range 1 to n, for j in range 1 to n. Okay, so now I'm going to loop through every element in my cumulative sum matrix S. I'm going to fill all of these in beyond the first row and the first column. Okay, so I'm going to start at row index 1 and column index 1, which are actually the second row and second column respectively. So here's where I could just apply this formula. So I can say, well, S at ij is equal to the min of S at I minus 1 j, S at I j minus 1, and S I minus 1 j minus 1, and then plus C I j. So whatever the best option was, whatever the best direction I could have come from was, plus, well, now I'm matching ij. Boom, that's it. So let's just look at this real quick. I can plot these two next to each other. So I'll plot the cross similarity matrix. Okay, so this is the algorithm. And look how short it was. Pretty nice, huh? So I can plot the cross similarity matrix. And I can also plot, let me put a color bar here. I can also plot this cumulative sum matrix, and we'll just look at it. So we understand that, okay, this is the, I say CSM for short, but cross similarity matrix. And this is, I called it the cumulative sum matrix. We understand that as the matrix which holds the minimum cost warping path from the beginning up to some place. All right, so here's what it looks like. So what we notice is if I ask you to construct a warping path down here that matches like the first 80 points of the point cloud but only to the first 20 points of the second point cloud, I can't do very well. I'm going to have a pretty high cost. Okay. But what you notice is this lower right element here. So if I print out S -1, -1, this is the lower right element. This happens to be the optimal cost over all warping paths. So let me check that actually. So if I use linMD2W, and I say path is equal to linMD2W.linMD2W y1, y2, and I sum up, so that was the optimal warping path. If I then, this is what you did on the last exercise, but if you got this far, you were paying attention and you deserve to see the answer. But, so if I sum up the cost, I could say cost equals 0 for I in range path dot shape 0, or I guess I can say length of path cost plus equals so actually hang on, let me say it this way, IDX, or no, I can do even simpler. I can say for IJ in path cost plus equals CIJ. So let's see what that cost is. Do we agree? Yes, we do. So linMDW returns a warping path that has this cost that we computed. Okay. So how do we find that warping path? I mean, this matrix ends up giving me in the lower right the cost of the optimal warping path, but how do we find it? So we'll work on that in class tomorrow, but I just wanted to get some of the prerequisites out of the way. Okay, very good.